In the previous two videos, we discussed the blade element momentum or BEM theory and its two most important corrections. The BEM theory is used widely in designing and optimizing wind turbine blades to maximize power output while maintaining structural integrity. For example, if you take a look at this particular picture of a wind turbine rotor, you'll notice that the blade is actually wider close to the root and narrower close to the tip. And so the shape of the blades is actually tapered, right? It's wider close to the root and narrower to the top. Another feature of the blade is that there is a twist along the span of the blades. So it may not be as obvious, may not be obvious on this figure, right? But I can tell you there is a twist along the blades. So the pitch angle at different radius or along different sections of the blade is actually different. So there is a difference. Once we have understood the BEM theory, we can understand why the blades actually look like this. This is a slide I copied over from the 8th video. This is a front view. This is the front view of the rotor plane. In previous videos, we were looking at the annulus ring with the radius r, and the airfoil located at this located on this vertical blade at this particular radius, right? And we were discussing the linear velocity, right? The linear velocity. Suppose the rotor actually goes this way, right? Then the linear velocity of this particular airfoil is capital omega. That's the rotational speed, right? Angular speed times the radius r, right? So the linear velocity is just the capital omega multiplying r. So that's the case if we do not consider the angular induction. If we consider angular induction, it's going to be slightly bigger, right? It is obvious that this linear velocity increases with radius. So as we move from the root of the blade to the tip, this linear velocity is going to increase. And on the next slide, we are going to take a top-down view to look at this airfoil, right? We are going to actually look at the cross-section along this particular vertical blade at different radius, right? But we are going to use this particular airfoil as an example. So this is a slide that I copied over from the 9th video, right? This really complicated diagram shows the different velocities, the wind velocity, the linear velocity of the rotor, the airfoil, the relative velocity, the different angles, and then also the different forces acting on this particular airfoil, right? So the linear velocity of this airfoil is shown on this arrow, right? This is the arrow for the linear velocity on this of this airfoil, right? It's capital omega times r. This time the angular induction factor is actually accounted for, right? So the angular velocity is so the linear velocity is slightly bigger. Right? So as we move from the root to the tip, again from the root to the tip, right? The radius r is going to increase, right? And so this linear velocity is going to increase, and there are actually two consequences because of this increase of the linear velocity along the radius. Because the incoming wind speed is fixed at the free stream wind speed multiplying one subtract the axial induction factor A. So this vector is actually fixed, right? It's not changing, right? So as we move from the root to the tip, the radius increases, so this linear velocity increases, so this vector becomes longer and longer, right? And it's still in the same direction, right? So as it becomes longer, the length of the relative speed is going to increase also, right? The length of the relative wind speed is the length of the linear speed squared plus the length of the incoming wind speed squared, and then take the square root of the whole summation, right? So that's UREL. So the length of the UREL is going to increase with radius, right? Because the linear velocity, this vector, keeps increasing with radius. Right? And a second consequence of increasing R is that as the length of this vector actually increases, the angle of the relative wind phi decreases, right? So as we actually increase the length of this vector, the length of this vector is a kind of fixed, right? So UREL is going to rotate. It's going to rotate this way. It's going to rotate this way. So phi is going to decrease. So as we move from the root to the tip, the angle of the relative wind phi is going to reduce. It's going to decrease, basically. Right. So from the ninth video, we also know that the normal force, dFn is what? dFn is this force. It's the force that's pushing back on the rotor. It's actually trying to push. It's trying to topple the wind turbine, right? It's in the same direction as the incoming wind. That's the normal force. Right? The normal force and the tangential force. The tangential force is actually the force that's creating the torque. Both kinds of forces can be computed from the lift force and the drag force. Right? They can be computed from the lift force and the drag force. And in the ninth video, we actually obtained the expressions for the normal force and the torque using the blade element theory. Right? These two expressions were obtained by bringing the expression for the lift and drag forces into the expressions for the normal and the tangential forces. So here CL and CD are the lift and drag coefficients, which can be found on a table, right? For different airfoils, for different kinds of airfoils. Those coefficients are actually tabulated. Right? Here C is the core length of the airfoil. And then capital B is the total number of blades. And the rho is the density of the air. So both the normal force and the torque, from these two expressions, we can see that both the normal force and torque increases with the square of the relative wind velocity. Right? So the torque also increases with R, with the radius. Right? And we know that the relative wind speed actually increases with R also. Right? So these two, both normal force and the torque, both increases with R, with the radius. Right? So if everything else being equal, the blade sections located at larger radius is going to experience higher normal forces and torque than those located close to the root of the blade. This kind of uneven distribution of the normal force along the blade can cause very damaging blade bending in the direction of the wind. And this is the picture. Right? The blade actually bends backwards. This is caused by this kind of uneven distribution of the normal force. Uneven distribution of the normal force along the blade. So close to the tip, the normal force is bigger. Close to the base, the normal force is smaller. If the wind speed is large enough, it's going to bend the blades backward. Right? And the uneven distribution of the torque along the blade can cause this kind of blade bending. The blade bending in the direction of the rotation, basically, right? So it's not sort of bend backwards in the direction of the wind, but bends in the direction of the rotation. So the torque close to the tip is much bigger than the torque close to the base or to the root. So again, if the wind speed is high enough, it may cause this kind of bending. It's also quite damaging. Right? So a straightforward approach to equalize the amount of loads along the blade is to actually reduce the core length. To reduce the core length with r, with radius. Right? So because the cross sections of the blades are actually airfoils, so reducing the core length of the airfoils with radius is actually the same as reducing the width of the blades with radius. And that is why the blades are tapered. Right? So it's wider close to the root and narrower close to the tip. So now let's think about why the blades are twisted. So again, this is a top-down view. This is a top-down view of the airfoil again. Right? So as we move from the root of the blade to the tip, the design goal, our goal is to keep the angle of attack alpha fixed at a pre-specified value. We don't want to change alpha, right? We want to keep alpha fixed, right, along the radius. We know that this angle of attack equals to what? Equals to phi, that's the angle of the relative wind. Subtract the section pitch angle theta, p. Right? And we know that phi actually keeps decreasing as we move from the root to the top, to the tip, right? The phi actually keeps decreasing because as we move from the root to the tip, this vector keeps increasing. The length of this vector keeps increasing, right? So REL is going to rotate this way, right? And that's going to reduce phi. But we want to keep alpha constant. So the only way to do that is to keep theta p decreasing at the same pace as phi. Right? If we can do that, then the angle of attack alpha can be fixed along the blade. Right? But why do we want to keep the angle of attack constant along the blade? Why do we want to do that, right? Again, we know that the normal and tangential forces can be computed from the lift and drag forces. And these are the expressions of the normal and normal force and the torque after we bring in the expression for the lift and drag forces, right? So the normal force only pushes the rotor backwards. It doesn't really do any useful work. It's actually the tangential force, the DFT, that's actually creating the torque, right? And that torque is actually doing useful work. It's actually rotating and generating power. So that's the force that's actually doing the useful work. So what we would like to do is to maximize the DFT. That's the useful work, right? Useful force, while minimizing the normal force. That's the DFN. DFN is not doing anything useful. It's just causing more damage or structural sort of stress to the turbine. So we want to sort of maximize DFT while minimizing DFN. So in this case, if we actually define a factor eta A equals to this ratio, right? So what we would like to do is to actually maximize eta A. Right? If we can maximize eta A, then DFT is maximized while DFN is minimized. Right? So after we bring the expressions for the tangential force and the normal force into this ratio, right, and then we do some algebraic manipulations to simplify it. Basically, what we are doing is just dividing the numerator and denominator both by DFL times sine phi. So we get a 1 here, right? And then you get this kind of ratio, and then cotangent theta plus this drag force divided by normal force ratio. The drag force over normal force ratio is the same. Right? And we also have the expressions for the drag force and also the expression for the lift force, right? And then we can actually just divide them. What we obtain is the drag coefficient divided by lift coefficient. Right? So if we represent CD over CL as epsilon, it's just a shorthand notation for this drag over lift ratio, right? Then we can write eta A as a function of epsilon. So at every radius, at every different radius, right, the phi, the angle phi, the angle of the relative wind is fixed, right? It's a given. given value. So eta A is basically just a function of epsilon, right? And if we actually draw this particular function as a function of epsilon, it's going to be monotonically decreasing. It's monotonically decreasing, right? If you don't believe me, you can just take a derivative with respect to epsilon, and this derivative is going to look like that. It's a cotangent square theta, and then cotangent theta plus epsilon squared. So this is a positive number, and then this is also a positive number for any reasonable values of phi, right? Oh, epsilon, right? So both of them are positive numbers, and then there's a minus sign in front of it. So the whole thing is like a negative number. So which means eta A is monotonically decreasing with epsilon, because the derivative is negative. Right? So it's a negative. It's a no monotonically decreasing function. So what we can do for this kind of monotonically decreasing function is try to find its maximum value, right? So when epsilon is at its minimum value, then eta A is at its maximum value, right? So we want to find the minimal value for epsilon. So if epsilon achieves its minimum, then eta A achieves its maximum, because eta A is a monotonically decreasing function of epsilon, right? So the lift and drag coefficients for different types of airfoils have been determined either through experiments or through calculations, right? Here's a plot of the lift-drag ratio. It's CL over CD. So it's just the inverse of epsilon. Epsilon is CD over CL, right? We want to find the minimum of epsilon. So in that case, we want to find the maximum of CL over CD, the lift-to-drag coefficient, right? And this curve basically shows you CL over CD as a function of alpha, the angle of attack, in terms in degrees, right? And this plot is for this DU93 W210 airfoil, for this particular airfoil, right? People have determined the lift and the drag coefficients at different angles of attack, right? And just by dividing those two coefficients, we obtain this particular curve, right? And at about 6 degrees angle of attack, we achieve a maximum for CL over CD, which means we achieve a minimum for CD over CL, right? So the minimum CD over CL is just at the angle of attack alpha equals to 6 degrees. So if we are using this particular airfoil as the cross-section for the blades, we would like to keep the angle of attack at 6 degrees along the blade, which requires us to change the twist angle along the blade, right? Because phi keeps changing. Now, once we have understood the shape of the airfoil intuitively, let's do a calculation for a specific example. Here we are assuming no wake rotation, so A prime is 0. We are assuming no drag, so CD is 0. No tip losses, so the Prandtl's tip loss factor is unity. The axial induction factor A is fixed at 1/3. If we bring those assumptions into the expression for the normal force provided by the blade element theory, right, we obtain a simplified expression for the normal force. On the other hand, we also have the thrust force provided by the actuator disk model, right? And because the axial induction factor A is fixed at 1/3, so we obtain this simplified expression for the thrust force. And in the blade element momentum theory, we were actually equating the normal force with the thrust force, right? And considering the expression for the relative wind, which looks like that, right? And then after bringing A equals to 1/3 into it, we obtain this expression, right? So after we have done that, we obtain this particular equality. We also have an expression for the tangent of phi. This expression was on the first slide of this, on the second slide, I think. So tangent phi equals to 1 subtract a divided by lambda r 1 plus a prime. Lambda r is the local tip speed ratio. Right? We have talked about the local tip speed ratio. It equals lambda times the non-dimensionalized radius. Right? So we have an expression for tangent phi. So we can just bring this expression for tangent phi into this expression. Just replace tangent phi with 2 divided by 3 lambda r. Right? And then we can actually solve for c, the core length. So the core length equals to this whole thing. Right? And then how do we actually get the twist angle, right? So alpha, that's the angle of attack, right, equals to phi subtract theta p. So theta p equals to phi subtract alpha. And we know that alpha, we would like to have alpha fixed at the optimal value. Right? And phi can be computed from here. Right? Phi can be computed from here by taking the inverse tangent function on 2 divided by 3 lambda r. Right? Phi can be computed. Alpha is given, and then theta p can be computed. Right? The section pitch angle. We know the section pitch angle. We know the twist. Right? So those are the expressions. If we want to sort of do a specific calculation, right, like this kind of thing, if we assume the lift coefficient, the CL, is 1, and then the optimal angle of attack we would like to fix along the blade is 7 degrees, and then the total number of blades, B, equals to 3, and then the tip speed ratio, lambda. So we need to use lambda here, right? Because most of the equations are expressed in terms of lambda r, right? That's local tip speed ratio, and lambda r equals to lambda times the non-dimensionalized radius. Right? So we need to know lambda. So tip speed ratio equals to 7. Lambda equals to 7. So once we bring those quantities back into this equation to get the phi, and then this equation to get the section pitch angle, right? Then we can actually graph them as a function of the non-dimensionalized blade radius, r over small r over capital R. Right? So this graph is for the core length. So for non-dimensionalized blade core length, that's c divided by capital R. Right? And then this graph is for the blade twist angle in terms of degrees. And then we can see both of them actually decrease as we move from the root to the tip of the blade.